So today we're going to talk about one of the most interesting things I think in calculus is the Riemann sum. What the Riemann sum does is it allows us to approximate area. So in particular, we're going to be able to find the area under curves for which we don't have some known geometric formula. So if I have, for example, this curve f here on the interval from a to b, this is the xy plane, we can use calculus to compute the precise area under this curve. Okay, so how do we do it? Well, you think about areas that we can find already, areas that we know. So if I have a function like this one here, which is f of x equals x. So just the line of symmetry, okay, and I'm interested in the area under the curve on the interval from 0 to 2. So on this interval from 0 to 2 under the curve, you can see that the curve naturally just forms a triangle. So it's really easy to see that we can find the area under this curve simply by using the formula for the area of a triangle, which is just going to be your area equals base times height divided by 2. In this case, our base is, so the base of the triangle is 2 minus 0, so it's 2. And then the height is also 2, since it's the line of symmetry. And so we get 2 times 2 divided by 2. So there's our area. Now, one thing to note here is that when we talk about area, I'm using this word rather loosely because it turns out that we can calculate the area under a curve, and sometimes the curve is above the x-axis, which makes it positive, makes the value, I'll call it a sum, which we'll see that it is. It makes the sum positive. It's above the x-axis, and the sum is negative if it's below the x-axis. So the term area it's right now I'm using it kind of loosely, and all of my examples will have a positive value, so we can refer to it as area. But it doesn't have to be. So all that to say that the area here has no units. It's a unitless dimension at this point. Let's say it's a unit squared. Now, we could find the area under y equals x, but what about something like this? If our function doesn't have a known geometric object, if our function is not the shape of a known geometric object, so if our function is not a rectangle or a square or some kind of a polygon or triangle, circle, something we have a formula for, then how can we find the area under the curve? And the way we do is we start with an approximation. So we find some representative object. In this case, we're going to be using rectangles. This is called a Riemann sum, named after the mathematician Bernard Riemann. And we're going to use that object. We're going to place it under the curve and then sum up the area of that object. And that's going to give us an approximation for the area under the curve. So it looks like this. Here's my example. I've got a parabola, y equals x squared, on the interval from 0 to 1. Okay. And what I want to do is approximate the area, estimate the area using 4 rectangles. So in this case, if I want to approximate the area using 4 rectangles, then I start here. So what I'm going to use here are called right rectangles, right endpoint rectangles, because we're going to allow the curve to intersect with the right side of the rectangle. Okay, so what we're going to do here is we're going to divide the distance between the endpoints and the number of intervals. So I'm going to take 4, I need 4 rectangles. So to calculate the width of each rectangle, I'm going to take 1 minus 0 divided by 4. Okay, so that's going to be called delta x. That's just the change in x. So the width is going to be uniform, which is going to make our calculation a lot easier. So each rectangle has a width of 1 divided by 4. The height of each rectangle is where the function intersects with the rectangle on the right-hand side. Okay, so we could find the area of these rectangles by taking 1 over 4 times the height of the function at this point, and then we add it up. Okay, so each rectangle has width delta x. The height of each rectangle is the point where the rectangle intercepts with the parabola. Now, let's look at how we can do the calculation. So we're going to get the height at each location. So f of 1/4 is the first location. We call this, by the way, we call this the 0th location. So it goes from 0, 1, 2, 3, and then 4. And we'll call this n sometimes. And then this one would be n minus 1. Okay, so we always start, when we speak of these as having an index, they'll always start at 0. Okay, so f of 1/4, that's index 1. And then I've got f of 1/2, 3/4, and 1. Okay, so that's going to give me all the heights. And each rectangle has width 1/4. So I've got height times width plus height times width plus height times width, like this. Okay, so we can factor out 1/4, and then this is what we get. Okay, so after we plug in the values into our function, we're going to get an approximation. It's approximately 0.46875, which is precisely 15/32. Now, what we can do here, and what's really amazing, and I think this is attributed to Riemann, is that we can get a better approximation if we have more rectangles. So right now we have 4 rectangles, but let's say we have we go from 4 to 8 rectangles. So over here, our estimation is 0.46875 using only 4 rectangles. Now we go here and we have 8 rectangles. We've increased the number of rectangles from 4 to 8. And on this screen, you can see I've got the actual area here, both sides. And as a matter of fact, on this side of the screen, I've got left endpoint rectangles. So here, the function is intersecting with the left side of the rectangle. And what that does is it produces an underestimation because the rectangles don't account for this amount of the area, right? And over here, of course, the right endpoint, because our function is increasing and it's shaped what we call concave up, it's going to have this feature that the right endpoint will be an overestimate and the left endpoint is going to be an underestimate. Okay, so anyways, what I want you to notice though is the estimated area and the actual area. So the actual area is 1/3, 0.333, right? Okay, so here we've got an underestimate. Here we have an overestimate, which is an improvement from just the 4 rectangles here. Okay, so if 8 rectangles is an improvement, what if we go from 8 to 16? Okay, so now we've got 0.3027 as our approximation on the left side, and then on the right side, we've got the 0.365. So we're getting closer to the actual area. So 16 rectangles is good. What about 32? Even better, right? You can see that between these two numbers, the difference is decreasing, the difference between the estimated area and the actual area. Okay, you can see that here. And so the idea is, well, how many rectangles can we actually put under the curve? Well, here I've got 128, and this is very, very good. And in fact, what's happening here is that we've got a more precise fit under this curve. So necessarily the width of the rectangles is getting smaller. That's the only way we can have 128 rectangles here, is if the width is shrinking as the number of rectangles increases, but we still keep the uniform width. Okay, so here with 128 rectangles, we have 0.329. On this side, it's still an underestimate, but look how close that is. And over here, we've got 0.33725, which is also still an overestimate, but still vastly closer than the 4 rectangles we started with. So the question is, how many rectangles can we use? And what would be the result of increasing numbers of rectangles? So to answer that question, we're going to go to the blackboard. This. Just a moment, and I'll switch my screen, and there we are. Okay, double check if there it is. Okay, so how many rectangles can we actually put underneath a curve? And the answer is we can put infinitely many rectangles. And what happens when we do that is that we get the precise area under the curve. So let me write this down here. We've got precise area under the curve. And I'm going to write of some function f of x on the interval from a to b. This is going to be given by this formula here. So we're going to take the limit as n goes to infinity. So n is the number of rectangles, okay? The limit as n goes to infinity of the sum from I equals 1. So we're going to start at 1 this time. Start at 0. That's fine. We'll start at 1, go to n, and then we're going to have f of x I star times delta x. Okay, and we're going to be using, well, you'll see here in just a moment. So this is called the precise area under the curve. It's also called a Riemann sum. Okay, so Riemann sum. All right, so in order to calculate the area under our curve, so let's take a look at our example. Oh, yeah, wait. I need two more pieces of information. So in this formula, you see delta x, and delta x is given by b minus a divided by n. And then you also see I've written this xi star. Xi star is going to be a plus I times delta x, like this. Okay, so that's all the information we need to be able to calculate the precise area under a curve like this. So let's take a look at the example we currently have. We know that we know what the answer should be. So we have f of x. Oh, let me write it like this. So let me use the language of a typical problem. Okay, so example, use Riemann sum to find the area under, and we've got f of x equals x squared on the interval from 0 to 1. Now, if it doesn't tell you how many rectangles to use, that means you need to do the process we're going to do here, which is take the limit as the number of rectangles goes to infinity. So let's go ahead and write down our equation. We've got the limit as n goes to infinity of the sum from I equals 1 to n. So that's going to be our number of rectangles. So what we're doing here is when I write this sum right here, this is saying I'm taking the sum of this product. I'm taking the sum of the areas of the rectangles. And how many times am I doing it? In this case, infinitely many times. I'm letting the n go to infinity. So actually, it doesn't. You can't ever arrive at infinity, but you can get. You can keep getting larger and larger and larger. Okay, so here we've got the limit as n goes to infinity of f of x I star times delta x. Okay, so we need to calculate our xi star. So I'm just calling it xi star to distinguish it from other xi's we've used before. So xi star is going to be a plus I times delta x. And actually that means we need to, I need to calculate delta x first, don't I? Okay, let me come back to that. So let's get delta x, which is going to be b minus a divided by n. So I've got 1 minus 0 divided by n, or 1 over n. Okay, now I can get xi star. Let me try that again. Strange looking x. There we go. Okay, so xi star. So that's going to be a plus I times delta x. So in this case, we get 0 plus I times 1 over n. So we just get I divided by n. Now, before I can continue this problem, I need to show you a special equation that we're going to use. So the way that we actually do this is we make a replacement. So consider this sum from I equals 1 to n of the first I squared integers. Well, a long time ago, there's actually a really interesting story about a mathematician named Gauss who figured out a way to calculate the first 100 integers using a shortcut, which is very similar to what I've got right here. So we can get this formula n times n plus 1. Let me make that more parenthesis-like. So I've got n times n plus 1 times 2n plus 1, and then divide that by 6. And so it's actually a lot easier if you multiply this through. So we're going to get n cubed divided by 3 plus n squared divided by 2 plus n divided by 6. So what does this say? This says if I want to sum up the first I squared terms, so where I goes from 1 to 2 to 3, all the way up to wherever n is, all I have to do, instead of adding up this infinite list, I can just plug the n into this formula. So if I want to add up the first squares from 1 to 1,000, I just plug 1,000 in here, and that's going to give me the value of adding up 1 squared plus 2 squared plus 3 squared up to 1,000 squared. Okay, so we're going to use this formula in our calculation here. Okay, so let's write down the formula. I'm going to use yellow again. So we're going to get the limit as n goes to infinity of the sum from I equals 1 to n. And this time our f of xi star, that's going to be, so where's my xi? It's right here, right? So I'm going to get f of I over n times delta x, which is actually just 1 over n. Oops. So delta x is 1 over n. All right. Now, what is f? F is just x squared. Remember? Where did it go? Didn't I wrote it down somewhere? Oh, yeah, there it is. So f of x is x squared. So that means I got to plug in xi star into that formula. So let's change the color again. So that means we're going to get the limit as n goes to infinity of the sum from I equals 1 to n of I divided by n squared times 1 over n. Okay, now all we have to do is calculate this limit, which is surprisingly simple when we use this expression the way I've done here. Okay, so first of all, notice that the 1 over n, it doesn't have an I in it, so we can take it out of the sum, okay? The only thing we need to leave in the sum is the terms that have an I. So I can go like this. I'll get the limit as n goes to infinity, 1 over n times the sum from I equals 1 to n. And then what's left in here is going to be I squared over n squared. And hold on, that looks kind of weird. And so again, I can take out the I. No, I'm talking about, I'm sorry, not the I. I was just looking at these two I's look curly, but this one looks straight. So I was like, what's happening here? They're all I's though, okay? The I's can be whatever shape they like, as long as we know what they are. Okay, so we can take out this n squared, and then I'm gonna have the limit as n goes to infinity, 1 over n cubed, right? And then multiply this to the sum from I equals 1 to n of I squared. Now, I know how to take this sum. I know that if I want to take this sum, this is equal to this expression right here, this guy right here. So what I can do now is just replace that sum. I can take the sum by replacing it with this formula. So this is going to be the limit as n goes to infinity of 1 over n cubed. Multiply this to n cubed over 3 plus n squared over 2 plus n divided by 6. Okay, now we're ready to take the limit, and you can see there's going to be some things that cancel out. So when I take the limit, I can see that, well, n cubed and n cubed will cancel out. So I'm going to get the limit as n goes to infinity of 1 over 3 plus n cubed and n squared. That's going to leave me with 1 over 2n. And then n cubed, did I say plus n squared? N cubed, 1 over n cubed times n squared over 2. That gives me 1 over 2n. And then 1 over n cubed times n over 6. That's going to give me 1 over 6n squared. Now, as n goes to infinity, as n gets very large, we're dividing this number 1 by an increasingly larger and larger, a number that's getting increasingly larger and larger. So as n goes to infinity, this term is going to 0. 1 divided by a number that's getting infinitely large is infinitely close to 0. And the same as this, also 0. So it turns out that when we take the limit, we get 1 over 3. And 1 over 3, well, this is approximately 0.3333. And if I make it ... then I can just replace the approximate with equals. And you can see that this is exactly what we got, or what we saw on the slide earlier. And I think another really interesting and worthwhile visualization is to take a look at this on the calculator. So let me just change my screen now, go to the calculator. And first I'll get rid of these guys right here. And then let's go ahead and plug this in, x squared. Okay, so there's my function. Now I want to adjust my window so that I can see what I need to see. And let's see, let's make that just from 0 to 1. We'll make the x from 0 to 1. That's what we want to calculate. We'll make this kind of a small. And then we're going to make the y value also from 0 to 1. So we'll kind of scale it down and see what it looks like. Okay, so there's our curve. Now this calculator is amazing. It will calculate and show us the area. So I'm going to do that using this calculator's area feature. Okay, so we're going to use this symbol down here, number 7. And it asks me for a lower limit. So I'm going to go over here to 0. That's where I'm starting. And then I'm going all the way to x equals 1. So hopefully I can actually get there. Sometimes you can get only close. Let's see. Yep, we got there. Okay, now when I click enter, it's going to shade in the area, and then it's going to tell us the value. And there it is, 0.333333. So of course, the 3's don't end here. This is just where the calculator's memory ends. Okay, well, I hope that was useful. Thank you for watching, and that's all for me.